Ladies and gentlemen, please welcome to the stage Jim Zemlin.
Good afternoon, everyone. Welcome back, and welcome to all of you who are joining us virtually. I am excited for this afternoon. We have two speakers coming out that need very little introduction. The first is Linus Torvalds, the creator of two things, Linux and Git. You might have heard of them. They've been used by a lot of people. He is joined by Dirk Hohndel, who is the Vice President and Chief Open Source Officer at VMware, for their annual fireside chat, which has not happened for 2 years. I can tell you confidently they're definitely wearing pants for today's event, and they're very excited to be here. So without further ado, please welcome to the stage Linus Torvalds and Dirk Hohndel.
Someone didn't read his prompts, I think.
No.
Let's see.
Jim is confused.
Jim is confused.
Oh, I thought we were doing that after. You just told me.
See?
All right. I got bad directions here, so it's technically my fault, but not really. We'll get through this. It's just the COVID thing has thrown us all off. We've got to get back in our groove. All right. I normally never do this with my wife, but I forgot to wish you a happy birthday. It's the 30th anniversary of Linux. This guy has for 30 years been maintaining now the world's most popular software, which if you think about that, it is both a little depressing, but also admirable in that, every 3 months there's a release, and it's doing the same thing for 30 years is pretty amazing. You pause to write Git, but we want to give you this birthday cake right here. That's right. You'll notice that there are no candles because that it would just be spittle of COVID right here. So in order to be responsible, we have a candleless cake, but we want to wish you a happy 30th anniversary. To all of the kernel developers, it really is a community also. Happy birthday, congratulations on 30 years. So thank you.
Thank you.
Thank you. Thank you. Okay, that was smooth. That went really, really well, as expected. Whenever you do little stunts like this, they have to just be perfect. So, hi, I'm Dirk Hohndel, and this is...
And I'm Linus, and this is what we do because I don't like public speaking, and this is about as public speaking as I'm willing to go for these days.
Yeah, and actually, so Jim was wrong. We did the whole thing last year in June for the Open Source Summit, and we did it over video, and it was terrible. And the thing that annoyed me the most was that when I looked at my screen, Linus was on this side of me. So when I wanted to look at him, I looked this direction. And then later I saw the video, and it turned out that in the video, the way it was around, I was always looking away from him. And it felt super awkward. So I like the in-person thing much better. This is admittedly, I think, the smallest crowd in front of which we have spoken in quite a long time. So welcome all of you who made it here, and welcome everyone on video. This is super exciting. So obviously everyone before this Q&A said to me, hey Dirk, you have to talk to Linus about the anniversary. So Linus, August 28th of 2011, you started Subsurface. What are your thoughts about this? Not
I should have seen that coming. Yeah, I know. No, it is 10 years since I started my third project, but it's not quite as well known as the other two.
Unfortunately, even though I personally am a huge fan of that project since I maintain it today, but I think what everyone wants us to talk about is Linux, of course, and you have redefined the birthday of Linux. Everyone used to use August 25th, and then you said, well, actually it's September 17th.
We've never had a very good and well-defined birthday, and I'm more than happy to just have the party continue for 6 weeks, because the first time it was publicly talked about and announced, per se, the code wasn't ready. And then when I did the first code drop, which was September 17th, I think, I still didn't think it was quite ready enough, but I had promised some people that I will make it available. So I made it available, but I didn't announce it publicly. And then the next code drop was the one that I announced. So there's like this 6-week period of wild partying going on every year when the anniversary comes up, because the birthdays just spread out.
Yeah, so October 5th was the actual announcement. And I think 01 was still called Freaks, right? That was before the name changed.
I went back and checked, and I called it Freaks, but at that point I had already been told that it was not going. The FTP site that I put it on, that I did not maintain, had a directory called Linux. Yeah. So I had actually changed the name in the kernel main make file to be Linux at that point.
Yeah, so Ari didn't like Freaks.
I am eternally grateful to other people for having more taste than I did, yes. So.
But I mean, as we look back to 30 years, obviously, what were your expectations? So when you talked to the folks at the university, when you made this first post, what was your expectation where this would lead?
So at that time, it was actually, I was at university, but it was never a university project. So I didn't really talk to anybody about this, except for I think I emailed like 5 people about the 0.01 release and said, hey, I put it up like I promised. And I expected it to be, I'd been programming, so I was 21 years old. I'd been programming for about half my life already at that point. And I expected it to be yet another of these projects where I do something interesting for the programming, and then it gets useful enough that you kind of see that, hey, I did something. And then you find a different project to move on to, because, I mean, you've proven your project, and now it's kind of done. It's not quite usable, but it's done enough that it's not interesting anymore.
Yeah, I mean,
and that was clearly then what open source changed, because suddenly this project that I probably would have left behind if it was only up to me, I started getting like questions about and eventually patches, and that just kept the motivation going. And here we are 30 years later, and it's still what keeps the motivation going, because as far as I'm concerned, it's been done for 29 of those 30 years. and every single feature ever since has been about things that other people needed or wanted or were interested in.
And a lot has changed. I mean, I remember when I sent you my first patches after 0.11 came out, you would rewrite all my patches.
Yes.
So he would absolutely not take code from people like me. So he would look at the code and then implement it the right way. And thankfully, at some point, you stopped doing that.
Well, I mean, that's one of the things, and I've seen it in other projects too, where people have this, especially when you start a project on your own, it is really hard to start taking patches from other people, because they're not quite to, I wouldn't say your standards, but they're not what you're used to. So for the first 3 or 4 months of people actually sending me patches, I would look at the patches and I would read the patches just to understand what they wanted done. And then I would rewrite the code entirely. And I might have continued doing that for much too long, but I'm fundamentally lazy. And at some point, I just decided this is stupid and would just start applying patches, which actually makes everybody so much happier because it's very frustrating as a developer to send patches upstream and then have the upstream maintainer, and I realize that now, I didn't realize that at the time, have the upstream maintainer basically throw your patch away and then rewrite it, and you go like, what am I? Chopped liver? It's not good for the community. So it's very important for a maintainer to just relax a bit and say, okay, I'm not this control freak person, and I actually want to spend my time on other things than rewriting other people's patches. But it's very important for community too. So laziness is a virtue in my book.
Yeah, this was one of those hilarious moments when I sent him a patch and he responded back and says, this doesn't work. And I foolishly said, did you try it? And he said, no. I read it. Okay, cool. But yeah, so your very early memoirs were titled Just for Fun. So you clearly started out as a project for fun. But at some point you got your first job offer, you got the first commercial interest in maybe not Linux, but in you as a developer. So when did that happen?
So that was, I didn't expect that question.
That's the whole point why I'm not telling you what I'm asking you.
So basically one of the things that Linux did for me, and I want to make that very clear, that people always thank me for Linux, and I'm like, you didn't get half of it that I got from it. One of the things that Linux did for me was, I learned a lot. But I also started the whole project to learn about the new PC I had and learn about all the features of the 386. And so I learned a lot, and I learned a lot about computer architecture and about the 386 in particular. And I got all these connections to other people through Linux. And there turned out to be a small startup company in Silicon Valley who was doing a clone 386 hardware. And I was one of the fairly small number of people who actually understands how the 386 really works. A lot of people kind of know how it works, but a lot of people don't understand how it works on a very low level outside of maybe Intel and few specialty groups. Mm-hmm. So thanks to Linux, I was something of an expert on the architecture, and I had the connections. So I had not finished my studies yet when I flew out to the Bay Area and got a job offer, which was wonderful because that's the only thing that actually got me to stop procrastinating and write my thesis and get my paperwork in order so that I could move to the US. So that's 23 years ago. No, that's 24 years ago.
Yeah, you moved here in 97, right?
Yeah.
Yeah. So this is interesting because you say you got a lot more than most everyone else. So who in the audience thinks that they have their job because of Linux? Yeah, so I think you're wrong with how many people.
But I have my job thanks to Linux too.
Yeah.
Right. And I'm paid quite well, and I get to do what I want to do. So, I mean, and I get to stand in front of hundreds of people and talk about it, which is not so great, but whatever.
But at which point did you think that you'd be doing this for the rest of your natural life?
That was a leading question. I don't know. I'm not so much Linux related. It was more like I was in Silicon Valley at the same company for 6 or 7 years. And that's when I realized that pretty much everybody else around me switched companies every 3 years or so. Mm-hmm. I mean, that's the Silicon Valley way. It's not universal, but it is pretty common. And I just realized I don't like doing that. I have these long-term projects, and not everybody is like that. That a lot of people find things that they've done for a couple of years, it starts to bore them, and they want to find something new. And it wasn't something where I realized that, okay, I've been doing this for 5 years, so I'll probably do it for another 5 years, and then another 5 years. It was more that I realized that I'm the kind of person who is boring and just wants to do one thing, and I'm a one-track mind.
So we talked about all the good parts of this. So are there any regrets that you have? If you look back over these 30 short years, the license, the allowing binary kernel modules, things that you shouldn't have merged, maybe fights with certain companies you shouldn't have picked. Are there any, I didn't say which companies, are there any regrets?
In the big picture, no. I mean, there's a lot. Everybody has small things that I should not have done that, right? There's a certain picture of me that certain technology news sources enjoy using
A lot.
15 years after the fact.
Yes.
And every single story is that one picture because they love that picture so much. And that's a small regret. And actually, I mostly find that funny. It's like, okay, I shouldn't have done that, but in the big picture, who cares? The bigger regrets are, they tend to be social. There's been disagreements where people had just said, this is enough. I'm going away. At the same time, I think that's something that happens to everybody, and I'm very proud of the fact that there's actually a fair number of people still involved with the kernel that came in 91. I mean, literally 30 years ago. I mean, Dirk is one of them. But considering how few people we were back then, the fact that we still have a handful of people that I can say, yeah, he was there before Linux was really even Linux. I think that's a testament to how good the community on the whole has been, and it's how much fun it has been. And I mean, you mentioned just for fun, but I mean, that's part of what I still strive for. So maybe, I mean, one of the things that people have talked about in the tech press a lot is how we're going to most likely try actually have kernel modules written in Rust, right? And from a technical angle, does that make sense? Who knows? That's not the point. The point is for a project to stay interesting and to stay fun, you have to play with it a bit. And I think finding things that may make sense for a technical angle where you can try something new and see maybe in the long run this will be a great idea. Maybe in the long run we won't even know because we will forget about this whole experiment is still important. I mean, 30 years later, the fact that I find technically interesting things to do in the kernel, I think is important, but it's also important that other people still try to do fun things. And that can be hard sometimes. And it can be hard because it used to be that we could just go wild and crazy. In 91, nobody cared. In 95, very few people cared. It was mostly used inside universities and places like that. In 2021, a lot of people care. So you kind of have to balance the having fun and making things interesting with the boring realities of many billions of devices running your code. So you have to find the fun where you can. But it's something I think we've been fairly good at. And that, I think, is, to get back to the original question, is something that is very much not a regret. That's one thing that I'm very proud of still.
And we have said this many times when we do this session. This is unrehearsed, so he has no idea what I'm asking him. And of course, then what he does to me is that he answers my next 3 questions in a long answer to the first question. So thank you for skipping over the next 3 topics. But I do want to double down on that Rust comment. So you have a, shall we say, interesting relationship to the security community, the people who focus on security.
How many people are security people? I mean, here, where you feel that your first job is security? Yes.
Okay, 5,
Yes,
6?
I will try to not be too harsh.
Thank you. And I mean, this is the newcomer, Linus, anyway. Yes. But so I was really intrigued by this idea of Rust kernel modules, because Rust is the golden project, pet project of so many people with a security focus. And I followed these discussions on the kernel mailing list and on other mailing lists on the challenges of getting the value that Rust gives you when it interacts with a kernel written in C. So I'm really curious for someone like you who is very much a through and through a C programmer. I was very surprised to see how open you were to this idea of introducing Rust modules to the kernel. Can you say some more about that?
So I really love C. I mean, there's no question about it. I think C is a great language, and C is, to me, really a way to control the hardware at a fairly low level, so that when I see C code, I can pretty closely guess what the compiler does. And still, to this day, I mean, it's literally not yesterday, but the day before, that I checked what the code generation was for one of the patches that I wrote.
So your love for C is similar to the people who are juggling chainsaws, right?
My love for C is the fact that it is so close to the hardware that you can do anything with it.
Yes.
It is dangerous. So I do see the analogy with juggling chainsaws. But it is a very powerful language, and it really gives you all the rope you need to create this beautiful knot.
Yes.
At the same time, because I love C, I also see that it does have a lot of pitfalls, and I know C so well that I see all the problems it causes too. The very subtle type interactions that are not always logical and that you take for granted when you use it so long are pitfalls for pretty much anybody. And they're easy to overlook, and in a kernel, that's not always a good thing. So you want the pitfalls when it comes to things like low-level memory management, where you're setting up the virtual memory map for a process and you're working on that level. But in many other situations, you don't want it. And Rust was the first language I saw which looked like this might actually be a solution to the other part of the problem, not the control the machine at the lowest possible level so that you can read the machine code and match it up with the C code, but to the problem where you just want to get the job done of writing a driver or a file system, and you're really working at a much higher level, even when you're interacting with the hardware on a different level.
But interestingly enough, the thread about the Rust kernel modules, of course, within days, started disassembling compiled Rust code and figuring out how it moved stuff around.
Yes,
so.
I mean, people still care about performance, and that's obviously one of the things that C gives you, that you can write bad code in C that performs really badly, but if you know what you want to get done, you can usually write C code so that it does exactly what you want. And then when people like that see Rust and see all the abstractions that Rust gives you, which do give you the type safety as long as you stay within the safe subset of Rust, those kinds of people get worried, and they say, how does this fit in with our worldview?
Yeah.
And there are a lot of people who care deeply about performance, and also, it's not just performance, it's also debuggability.
Yeah.
When we see bug reports from people, and it's a null pointer dereference, and the bug report comes with the register dump and a call chain, you want to make sure that you understand what the compiler does so that it all makes sense to you so that you can decode the bug and bug report and figure out what's wrong. So there are many interesting challenges in this area, and people have been talking about Rust in the kernel for a longish time by now, and it's not done yet. Yeah. So we'll see. Probably next year we'll start seeing some first Intrepid modules being written in Rust, maybe being integrated in the mainline kernel.
That sounds exciting. So you mentioned that you are a C programmer at heart, and in this merge window you did something that made you super popular with your maintainers and with yourself, which was the introduction of the W error to the compiler, which was...
It's actually, it's been interesting seeing what the split has been in the community, because there's a lot of people who quite reasonably say that, hey, warnings are warnings and they shouldn't be errors because they're not so important. That's why they're warnings, right? So you shouldn't treat warnings as errors. And at the same time, and I understand that completely, because if I see a warning that I think is the compiler being wrong-headed about it, I will turn that warning off. But at the same time, in my tree that I have maintained, in the configurations that I look at, I have not accepted any kernel warnings during the build for the last 5 years or so. And in the last merge window, I basically got tired of people sending me things that added new warnings, because it had been tested, but it had gone through a number of automated tests that didn't check for new warnings. And I said, enough is enough. Now I'm making my rule be everybody's rule, and said that we are building the kernel with warnings being errors. And it's actually taken about 3 weeks since then to fix up almost all of the fallout. And I say almost because we still have Clang in particular will warn in a lot of configurations. And we still probably have a lot of these odd configurations where people haven't quite sent me all the bug reports about, hey, now this random configuration warns in this situation. So it will probably take a few more months before we're really clean, but right now we're so clean that no normal configurations should not notice. So
we talked about the 30 years. We talked about the fact that when we started and we both were a little younger, hardware was very different. We were in the 386 days. My first Linux box had 2 megabytes, megabyte with an M for those younger people here, of memory. And so it was a very different world. When I first got Linux, I printed out the full kernel sources because I wanted to read what's in there. I don't recommend doing this today. But so when we started, it seemed really easy to get into a project. It all seemed very manageable. It seemed possible to get an overview into a project. If I look around today and you build a quick little Kubernetes thingy with a couple of microservices and a few containers and use a couple of S3 backends, and you have no idea what's actually running on your computer. So if you were starting today, what do you think you would be working on? Is there something where you say, ooh, this is cool, that's what I would be doing? Or do you still think I would write C code for some microcontroller?
I've always been, the reason I'm doing kernels is I've been interested in, I'm a software engineer, but at the same time, I'm mostly interested in what the hardware does. I've never been so interested in the end result, right? To me, it's been the controlling the hardware to do something and understanding what's going on. That's the most interesting part. And that's why I've been interested in compilers, and obviously operating system is like the real example of controlling the hardware and understanding how the hardware works. But I also grew up in the situation where home computers, this was before PCs, where home computers were something that were so simple that you actually could understand them, which is not true anymore. So I can't really answer that question for the reason that the person I am today I'm interested in the hardware side, and I'm interested in the operating system, and I would do compilers or operating systems. But if I grew up today, I'm not sure if I would get close enough to the hardware where I would feel comfortable understanding it. But on the other hand, the other side of that coin is there's so many more resources today that really were not, I mean, the world was simpler back then, but it was, the internet really has changed how easy it is to find stuff. To learn about the 386, today, what you do is you go online, you go to Google, and you type in 386 architecture manual, and you will find it. I ordered mine from Denmark because it didn't exist as a book in the bookstore that I had access to. So it had to be ordered from a different country just to get the manuals for the hardware I had. So some things have gotten so much easier that I don't actually know whether maybe hardware development isn't that hard after all. You have Raspberry Pis, you have all these microcontrollers that are much more accessible than they were when I grew up.
Then if I turn the question around, if you look at the projects that are out there in open source, there are millions and millions and millions of them. Do you have this wish list, this, I wish there was a project that did X, this thing?
I'm very happy to say no, because that's how I get suckered into doing something myself. To be honest, my needs are very, very limited. I use computers mainly to read email and do Linux programming. So there are very few projects that I feel are needed because all my needs have been fulfilled a long time ago. I mean, the last one was literally 10 years ago when I looked around and could not find a scuba diving log program. So I had to write my own.
As one does, yeah.
As one does. I mean, this should be how everybody works, is that when you notice that there's something lacking, instead of whining and complaining about it, like, not naming it, you just do it yourself, right? But at the same time, you know, I'm very happy with where open source, and not just open source, but the technology landscape in general is.
I think on that marvelous comment we should end this session. So if I look around here, clearly we can do Linux events with fewer people. And one of the things that Angela, the senior VP of events at the Linux Foundation, always loves when I do is solicit ideas where we should have the next event. So I'm thinking it's a couple hundred people here in the room, so we should go to Palau or maybe Fiji or I don't know, Hawaii. Yeah. See, yeah. So can we have a vote, a quick vote here in the room? Palau? Fiji? Okay, Fiji is okay. Angela, get planning. In the meantime, so we've been doing this for a while. It's been 30 years, so we plan to be back here in 2041 for the 50-year celebration, both of us in our 70s, or should we make nearer plans?
I don't, people usually ask me about the technical plans, and I say my technical plans, I look about 6 months out. I know what's going on the kernel side. My personal plans, about the same, right? I've been very happy doing the kernel for 30 years. Somehow I don't see myself doing kernel programming when I'm 70. But on the other hand, I didn't see myself doing kernel programming when I was 50 either, a few years back. So we'll see.
Thank you so much. We'll see you next year for the 31st anniversary in Fiji. Thanks, everyone.
All right. Hold on a second here. I have a quick question for both of you.
Okay.
Fiji, that's a tough venue. It could be costly. So I'd like to make a proposal.
Okay.
On the 30th anniversary of Linux. If we could take the 1991 email make an NFT. Auction it off. Just for reference, the first tweet NFT, 6.5 million, which I believe was paid for in Ether, which is now worth 20 million.
Okay.
What do you say?
I'm staying out of the whole craziness with crypto and NFTs. I'm like, those people are cuckoo.
Oh,
It was a good try.
all right. Well, I'm going to keep working on this. So, maybe for a better cause than going to Fiji. If we have a good charitable cause, think about it.
All right.
30th anniversary NFT. Thank you both.
Thank you.
Thank you.
We got to keep asking them about the NFT. Our next speaker needs also very little introduction. Chris DiBona is the head of open source and maker science at Google. He is also one of the original creators of an open source program office at any company. And for those of you here attending OSPOCon know that Google has done one of the best jobs of creating a very systematic, structured, intentional approach to open source. Chris is going to come in today and tell us about what it means to be an OSPO and how they help support open source projects. Please welcome Chris DiBona.
So first of all, you know what I say when people say, oh, who was the first open source office? I was running a little community marketing team for then Linux, hardware vendor VA Linux. And Christine Peterson, Tim O'Reilly, and some other folks came by, and they came up with this name for this thing we were doing, and that was open source. So I like to just give credit to Christine as the progenitor of all of these groups, and give her a lot of credit for the movement. So that's what I'd like to say about that. So it's always fun to follow Dirk and Linus. So I won't be upset if you go to the bathroom or something, because the headliners done their thing. If anything, I should be like the comedian they bring out before the rock band comes out. And it's funny because I even pre-recorded this in case COVID screwed everything up. So whatever I do kind of doesn't matter. So if the pre-recorded one's better, we'll just put that up for the video audience, right? So there's no pressure, and that's great. A couple things about what Dirk and Linus were just saying. I always found C as like the mother's milk for me of programming. It was the closest thing I had to being able to see the electrons moving over the traces on the motherboard, right? So when I found C, I found computer science, I found inner peace, and when the Rust announcement came out, I was pretty surprised, but it makes a lot of sense in some ways. But we'll talk about that maybe a little bit later in the talk. Reflecting on the birthday of something like a kernel seems a little unusual, but it was 1998 when I went to Linus's house and recorded an interview which we synthesized into their chapter in a book we were writing at the time. And I'd like to think that we've both aged really well. So I video recorded it. So Linus doesn't know this. So we video recorded this, and I think I should put it up on YouTube because it's pretty funny. Anyway, so happy birthday, Linux kernel. So what's funny, back in 2007, it was that was the 26th birthday or the 16th birthday? Anyways, right when the 16th birthday hit, we were like, wow, Linux can drive. That's very exciting. We had all these dumb jokes about it can drive, and then it can drink at 18 or 21, depending on what country you were in. And look at this little operating system that could, right? And I was thinking about that in the context of 30 years, and I was like, well, wait a second, in 2013, we had a Linux-based robot, and we were watching it on the ISS move from module to module with its little impellers that were powered with CO2 cartridges. And that was basically running an Android, which was running Linux, and it was moving it around the ISS. And this was a time when Linux was already actively driving cars in what would become our Waymo division. And we also knew about orbiters from Planet that they were shipping up running Linux in their CubeSats that are taking pictures of every spot on the globe every 3 weeks. And then it turned out that it was also being used on major satellites. It was being used on the most recent Mars rover and in instruments processing all that data here on Earth, in orbit, and on other planets. So it's not like Linux can drive a car, ha ha ha, maybe we'll take it out for a beer. It's literally an interplanetary operating system. It's not survived, it's thrived, and it's kind of remarkable, right? And so when you have something that important, that omnipresent in hardware and in computer science, it's going to be around in 30 years, but can it thrive and continue to be vital? So before talking about what I think the future is, I wanted to tell a story about the past that a lot of people haven't heard before. So when we had just bought the Android company, and I think that Chet Haas talked about this in his book, we weren't 100% sold on the idea of going with Linux as the underlying kernel. The Danger folks who had gone on to form Android, they were used to NetBSD. It's what they use as the underpinnings for the Sidekick. And so we were talking about what was the right path forward for a cell phone operating system, for a mobile operating system, that we were going to be throwing all this weight behind. And we decided that Linux was kind of the only choice. Because at the time, we knew, ARM was single-threaded, it wasn't pipelined, it was a very basic chip. But we knew that we were going to look at a future where there was going to be multiple CPU cores. I mean, we thought multiple chips on die, but there were going to be multiple CPU cores, there were going to be more advanced buses, more advanced memory architectures. And we thought that, BSD's good, but Linux is already going in these directions. It had this really fantastic approach at letting competing architectures, competing approaches sort of exist at the same time. See which ones work better, which ones should be re-mainlined. It had this really terrific approach to evolving to new platforms and new platform demands and new user demands. We sort of, famously for nerds, don't know if everybody knows this, but we came up with a scheme to allow the Linux kernel to more aggressively manage the battery and power consumption of applications. And this was called wake locks. And when we introduced it, a lot of kernel developers hated it. And some of our competitors were like, why are you forking Linux? And I was like, yeah, well, we're absolutely forking Linux. This is exactly how you are supposed to take open source, take it in a certain direction that's experimental, and then see how it works out, and then reintegrate it back in the mainline. Might take years, but that's the path. And so, and that's kind of exactly what happened. We came to a place of compromise with the kernel team around wake locks, and as a result, let's be clear, at the time we were maybe shipping on 10 million handsets, and now Android is sitting on 3.5 billion devices. So Linux's ability to anticipate where the industry is going and adapting to it is what makes, I think, Linux not just the platform of choice today, but the evolving platform that we're going to be looking at for decades and decades. There's another thing too, and it's not very popular to say it, but there's an old thing where you would never get fired for choosing IBM or whatever. You're not going to get fired if you picked Linux, right? And the worry of this is that is Linux going to lose its edge? Is it not going to be hungry for user demands anymore? Because it's not good to be too big to fail, right? And my hope is that that's not going to happen. So how can we keep it from happening? So first of all, there's a couple of things that we have to address as a community, right? We made it to here because we were flexible, because we were expansive, and we even looked prophetic in where we were going with the kernel and what it was going to support, right? We were looking at what wasn't working, like for instance, VirtIO about 4 years ago. Bad performance, not flexible, and we went through this huge process, and now eBPF is coming in as a way of addressing that at the kernel level all the way through to VMs. It's like, if you just keep an eye on how people are using your software and you adapt, you will persist, right? And so I guess what I'd say is what's on people's mind today? What's today's VirtIO? What's today's wake locks? What's today's multi-CPU architectures that made Linux so popular when it just came out, because it had an eye towards the future? And I would say, and probably predictably, given the content of the keynote yesterday from Jim and from all the people, it's security, right? So, what's on everyone's mind? How do we get through the next 30 years? It comes down to a couple of things, right? For lack of a better word, we kind of need to up our game on how we're approaching security. So I don't know how many of you have been keeping up with what's been coming out of, say, the Biden administration or the United Kingdom on their guidance around supply chain security and what it says about open source software in there. But it's really important, not because of where it's coming from, but because of where we need to go as a kernel, as an open source software community of developers and adopters, but also as an industry, in the computer industry. We have to change, frankly, our ways and become not more accountable per se, but we have to have a better understanding of where our software is coming from, who's putting it together, what we're depending on, who's building the software for deployment, and then for release to the user, whether it's as a web service or as an application on your phone, or anything. So the Linux Foundation, as you might expect, this being a Linux Foundation show, has stepped up and said, hey, maybe we can have something together that we do together. And that's the Open Source Software Security Foundation, or supply chain. I'm bad with the acronyms. But long and short of it is, we created the OpenSSF, and we adopted some of the old scorecards that came out of CII and improved them. And then there you go. We're taking an eye towards supply chain security there. I think it was just yesterday that they released their disclosure guidelines, which was worked on by Anne on my team and some other folks on my team, which I'm very proud of the work they did. And people from other companies too, sure. But they have an eye towards what it means to secure your chain of dependencies. So at Google, we released a site, it's called deps.dev, and I believe it covers Go, Python, Node.js, and I think more coming. And what you can do is you can basically go to there and say, okay, what am I depending on, and how's it doing? You know, are there any outstanding CVEs, any outstanding problems with security that I should know about, and that I can communicate to my users? So here's the thing. I'm not as good a software developer as Linus and Dirk. But I can also guarantee you that they would tell you this too. All of our software is insecure. There's never been a piece of software that is perfect. And our measure as developers is not, and if we can ship perfection, because none of us can. There's always going to be somewhere that needs improvement. Our measure as developers, as users, as adopters, as people who ship software to our users, is what we do when we find out we have a problem. And so we have disclosure guidelines. We have guidance that we can give people. But if we, as a developer community, as a kernel community, can say, okay, let's have these processes in place so that when there's a problem, we fix it, and that fix is tracked throughout the chain of trust, then we're going to do great. And open source will have a bright future because we're going to anticipate where the industry, our users, and everyone is going. We're going to adapt as we need to be there for people so that when they decide, you know what, I want to try this new platform, I want to try developing this new architecture, Linux, open source software is there for them to start with. And then as stewards of these incredibly important software infrastructures, everybody in this room is looking after something that matters, right? We can say, hey, you know what? Open source is the right path because we are the best possible stewards of our software for now and for the next 30 years. So I don't know if I'm going to make it to 80 or 79. Given my family history, I'm not sure. But if so, I'd love to see you all. I'll probably have like really white hair, and I may be sitting down giving a talk like this. So that's it, and happy birthday to the Linux kernel, and thank you to all the Linux kernel developers who may watch this speech. It's a hell of an achievement, and I'm glad to have been a small part of it. So thank you.
Thank you, sir.
Sure.
Okay, our next speaker is going to be virtual. The next speaker is going to be talking about machine learning and research at NVIDIA. Anima Shri Anandkumar is the Ben Professor of Computing at the California Institute of Technology, and she's going to talk about tensor methods for machine learning. Please roll the virtuals talk.
Welcome to my talk on tensor methods for machine learning. When we look at rich data that we have today, they're inevitably expressed as tensors. Whether it's spatiotemporal data or LiDAR and other higher dimensional data, you want to express them in multiple dimensions. And that's where the language of tensors is very powerful. And so when we think of tensors, they're nothing but generalization of matrices to more dimensions. So when we think of scalars, right, they're zero-dimensional. Vectors are one-dimensional, meaning they have a length and a direction. Matrices have rows and columns, but also they are linear operators, meaning you can define a subspace, you can multiply two matrices, and that's the foundation of linear algebra that we have today. And so tensors are extensions of this to more dimensions. So when we are now thinking about an array with more than 2 dimensions, you can think of that as entries of the tensor. But also more importantly, there are rich set of operations we can use to extend matrix products, matrix eigenvectors to now more dimensions and be able to process the rich high dimensional data that we obtain in many applications. And tensors are now the next big thing. And why is that? It's a natural progression, right, from the scalar thinking we had in the 1960s to the revolution of linear algebra that brought us matrices and the ability to parallelize matrix computation. And now we are at the level of having block matrix operations in our deep learning systems. Whether it's on GPUs or other hardware, we have rich primitives to speed this up and to parallelize this. And the natural progression here is to now also incorporate tensors with arbitrary number of dimensions and be able to parallelize them effectively, as well as design good primitives and good algorithms with that computational advantage. And that advantage of tensors we show is available for deep learning, whether it is the ability to compress very large models with a much smaller number of parameters without sacrificing accuracy, or getting speedups, as we mentioned with tensors, we can parallelize more effectively and hence get much more efficient primitives. Or generalization, we'll look at generalization not just within a domain, but across domains. And tensors have good inductive bias to incorporate the multidimensionality in the underlying data, and hence can also generalize better. And finally, robustness, right, is related to generalization. We need to be able to handle different kinds of noise and corruptions, and that we show with better inductive bias of tensors is also more effective. And the tool we are incorporating all these operations is called TensorLi. It's an open source high-level API which connects to a large family of backends. So the whole idea is in order to be able to work with tensor methods, you only need a high-level Python API that TensorLi provides, and then the details can be handled with different backends. And the idea is we build on a foundation of a core set of tensor operations, which I'll show you some examples in a minute. And on top of it, we do sophisticated tensor methods like decomposing tensors or regressing on tensors. And then at the very top, we have TensorLi Torch, which is specialized to PyTorch, but is able to have ready-made layers that you can directly incorporate in your deep neural network without having to have any additional coding or any additional design. And so you see a hierarchy of operations available, and this is open source. I encourage you to go and download the tool and the notebooks that come with it to easily get started. And so one of the core operations in tensors is the extension of matrix product to more dimensions. Just as you can multiply two matrices, you can also multiply two or more tensors. And this pictorially shows how that tensor contraction is an extension of matrices. And you can do this along the different modes or different dimensions of the tensor. And these are operations that you can easily define in TensorLink. And it's this also known as the N-mode product. And similarly, we can think of decomposing a given tensor into its components. The CP decomposition is a natural extension of matrix eigendecomposition to more dimensions. And you can just have a single line of code here to do that in TensorLink. And this is a building block on many different operations, right, where you're starting with a tensor and you want to find its principal components. And in fact, this is one of the core operations required in topic modeling, where we want to extract topics from the underlying documents in a non-supervised manner. So let me give you some of the recent projects we've been doing on incorporating tensors into deep learning methods. A natural way to do this is to start with a matrix layer, right? Any a linear layer here, and you can convert that into a tensor. In this example here, a third order tensor, and then further factorize it into low rank components. And with this, you're able to effectively compress the number of parameters in the tensor and hopefully still not lose accuracy, because the tensor rank, being low rank as a tensor, is still much more expressive than having a low rank matrix. So we're getting better expressivity with tensors without sacrificing the compactness. And in one of the first papers we did was to show how we can replace the traditional fully connected layers in neural networks with a tensor regression layer. So in this last layer, we can now convert it into a regression layer where the weight matrix is expressed as a low rank tensor, and hence can be much more compressed than in the standard layers. And by doing that, we can get similar accuracy with as much as 65% space saving. So you can have much smaller set of parameters while having the same amount of accuracy. That shows that these kind of tensorizations have good inductive bias with the underlying structures. And another example is being robust to noise, all kinds of noise, right? Whether it's different kinds of corruption or even adversarial noise. And in one of the works we did with the MRI data in the 3D setting, what we've seen is by replacing the linear layers with the tensor regression layers, we can get a much better error. And additionally, if we are doing dropout on the tensor components, we can be even better in our robustness. So this shows that there is good inductive bias in these tensor architectures, and you can seamlessly integrate it with neural network architectures. And so to make this seamless, what we did was to build a PyTorch-based TensorLink torch, where you can directly define the layers in a neural network with simple commands, and then be able to come up with entirely new neural network architectures. For instance, if you want to factorize your convolutional layers, what you need to do is simply specify the different parameters like rank. It's just a single line of command, and this is treated as just any other layer in PyTorch. Or if you want to start with a pre-trained layer, because many times we have pre-trained models and there is no need to train from scratch. Instead, we can try and compress those pre-trained layers with tensor factorization. And so that's where you can see here, this command will help, if you specify how many parameters you want to reduce, what is the fraction of parameters you want to keep, that you can incorporate into now fine-tuning with tensor factorization. And you can also do that using multiple layers, not just one layer. And you can also create tensors in the linear layers, right, or fully connected layers, and also incorporate different kinds of factorization. And similarly, for the last layer, it's a regression layer. We can again describe what kind of input and output shapes you want and what level of rank or compression you like in these layers. So as you can see, these are all simple, easy to specify layers that can be directly incorporated into your PyTorch training. And lastly, also the ability to drop out on tensors. So just as we have dropouts in standard neural networks, with tensor dropout, the ability is to go and directly have dropout on the factors of the tensor, and hence be incorporating much higher level of robustness, because you're dropping now entire components. So you have to be much more robust in order to handle that. And that's the kind of flexibility we have in TensorFlow in being able to incorporate all these different kinds of regularizations and tensor layers. As an example of this, we did a large-scale video classification study using kinetics. This is the large-scale benchmark that is standard for video-based prediction. And the standard pipeline is to go from ImageNet to kinetics and then fine-tune on various tasks. And what we did was we started with the pre-trained PyTorch kinetics model and then compressed it with TensorFlow. And again, we just used simply the convolutional layers and compressed them. There is much more room for overall compression. But even with that, what we see is a promising rate of compression without loss of accuracy. And similarly, with the ImageNet setting as well, we can get even better accuracy while having a good compression rate compared to the standard models. And as you can see, if you're trying to factorize multiple layers together, you get even better compression rates. And so far, I showed you the advantage of tensor methods for deep learning. Another setting where tensor methods are very promising is for large-scale quantum optimization. And this has been a recent endeavor with Taylor Patty and Susan Ellen from Harvard, and an interdisciplinary project bringing together tensor methods and quantum algorithms. So indeed, the promise for us is one day we'll have these powerful supercomputers, right, with very high entanglement. But that kind of quantum supremacy is not anytime soon, right? That's what most experts will agree is the case, that this is extremely difficult, if not impossible to achieve. And in the nearer term, what seems much more tractable is these what we call variational quantum computing, which have a moderate level of entanglement rather than the highest possible entanglements. And what we want to explore is whether we can solve various useful problems such as combinatorial optimization or quantum chemistry using these circuits with moderate levels of entanglement. And one such setting is to, say, incorporate combinatorial optimization methods like the max cut problem, right? This is a standard problem in combinatorics. And what we can do in a standard way is to incorporate the graph and its weights, which we want to optimize classically, into a quantum circuit. And then we can do variational optimization on this quantum circuit, right? And then get the final answer, essentially what is the max cut from the ground state of the Hamiltonian. So this is a standard setup for variational quantum methods. But what we wanted to go beyond was to ask in this kind of encoding, right? So can we encode our max cut problem in a creative way into the Hamiltonian of quantum circuits? And the second one is what kind of quantum circuits can we design efficiently that we can simulate in our classical computers on GPUs efficiently? And for the second question, the answer is with these kind of tensor rings or matrix product states where there is only connectivity amongst nearest neighbors is easy to incorporate because the tensor contractions involved here are only local. And hence, these are efficient to simulate on GPUs, but we wanted to ask how well can they solve hard combinatorial problems like max cut, and is there a quantum advantage by even incorporating simple circuits like this tensor ring with only small levels of entanglement? And the answer is affirmative. What we've shown is as high as 512 qubit circuit, and this being able to solve with a high level of accuracy these hard max cut problems, right? So showing that we are able to solve this on just a single GPU, i800 GPU, we can solve these now large graphs, large circuits, which is not possible if you're doing the high entanglement quantum circuits. And at the same time, we can have efficient algorithms that can have the number of required qubits by encoding both what is known as the X and Z spins, and then getting the results of max cut through a nonlinear optimization. So this is new in terms of algorithm, but also what we are seeing is the ability to use tensor contractions at scale on GPUs and be able to solve these hard max cut problems at scale. So I gave you a short overview of tensor methods, both in deep learning and now more recently, what we can do with scaling up quantum algorithms on GPUs effectively. And hence, in future, we'll continue to develop these methods. I encourage you to go check out TensorLee and the notebooks available with it and start contributing and participating in this ecosystem.
All right. Thank you, everyone. This concludes our afternoon sessions. We have a brief break before breakout sessions begin at 4. We are going to have birthday cupcakes and other refreshments at the sponsor showcase, so head on down there. Tonight at 5:50 we have reception, also at the sponsor showcase, and we will have 2 book signings. One, Gordon Half is going to be signing his How Open Source Ate Software book, and Frank Vasquez will be signing Mastering Embedded Linux Programming. So please come on down, get your book signed, and enjoy the rest of the evening. We'll see you again tomorrow. Thank you.
Every time you come around, you know I can't say no. Every time the sun goes down, I let you take control.